and I've been a professional in the IT industry since 1995. With a primary focus on technical training, I can be found most of the time producing and delivering learning content centered around network infrastructure and services. I've also been involved with extensive practical implementations in a variety of operational capacities, including architecture and design, deployment and implementation, administration and management, and various other technology-based roles. Wireless networks are much more versatile than wired networks, especially in an environment where running wires might be difficult. In this course, we'll examine the most efficient wireless networking protocols to use in various situations. I'll begin by exploring common wireless frequencies and channels and discover how to differentiate between the 802.11 standards, including A, B, G, N, AC, and AX. I'll also explore considerations when working with long-range fixed wireless, including licensed, unlicensed, power and regulatory requirements, and discover features of near-field communication, or NFC, and radio frequency identification, or RFID. I'll move on to cover common server roles, including Domain Name System, or DNS, and Dynamic Host Configuration Protocol, or DHCP, and discover the global market for Internet of Things, or IoT, end-user solutions. This course will help to prepare learners for the CompTIA A+ Core 1, or 220.11.01 certification exam. Strength and intensity, it could still operate on the 2.4 GHz band with improved range, so it remained backward compatible with 802.11b or G, both of which used the 2.4 GHz band. So then, in terms of the pros and cons for N, on the plus side we now have the fastest maximum speed and the best signal range, and again, because it was a more intense signal, it was less prone to interference. On the downside, again by today's standards, N is starting to become out of date, and since it is still using the 2.4 GHz band, interference can still be an issue, but it was certainly less prone than its predecessors. 802.11ac arrived in 2014 and was also referred to as Wi-Fi 5, and one of its primary features was significantly improved speed, offering a practical range of at least 433 megabits per second up to and over 1 gigabit per second. But to achieve this kind of bandwidth, AC operates exclusively over the 5 GHz band, making it effectively incompatible with earlier versions. Now that said, I do want to make a clarification here. With the release of 11AC and its inherent lack of backward compatibility, many manufacturers started to release Wi-Fi access points that offered dual-band transmissions, meaning that the Wi-Fi router could transmit over both the 2.4 and the 5 GHz bands at the same time. Now that said, it did not mean that any given client could connect using both. Rather, if you had a mix of clients, some using 2.4 and some using 5, they could both connect to the same router at the same time, with each one using its appropriate frequency. So this may have led some to think that 11AC defined the ability to use both bands, but that's not really the case. If you have a dual band router, and if you're using 11AC, then that specification still uses the 5 GHz band and only the 5 GHz band. So once again, largely incompatible with earlier standards. If it's also transmitting over the 2.4 GHz band, then it is most likely providing the specifications of 802.11n, which itself is backward compatible with B and G. So again, it's not that 11AC defined any kind of standard whereby either band could be used. It was simply due to the fact that AC itself has minimal compatibility that many routers started to offer both AC and likely N or older in the same unit. Okay, but it was still transmitting those two separate standards. Now I should also mention that AC itself is compatible with A, which also used the 5 GHz band, but given the almost 15-year separation between A and AC, I would say that it's quite unlikely that you would see any devices these days still using the A standard. So bearing all of that in mind, if we run down the pros and cons, on the plus side, the primary benefit of AC is its improved bandwidth, which was achieved through some enhanced transmission techniques such as wider channels than other methods and a process known as beamforming, which more directly focused the transmissions, both of which helped to maintain the higher bandwidth even when many devices were connected, and the dual band capabilities, but again, that was more so an option of the manufacturer, whereby anything using the 2.4 GHz band did provide for backward compatibility, but in that case it was over 11G or other 2.4 compatible standards. AC itself is not compatible with anything on the 2.4 GHz band. Hence, on the downside, for AC on its own, it is effectively incompatible with the earlier standards, with the possible exception of A, which in practical terms is simply out of date. And finally, in 2019, AX was introduced, which is also referred to as Wi-Fi 6, and like almost all newer standards, it offers significantly improved performance with speeds approaching 10 gigabits per second, and like its predecessor, it also often provides for dual band transmissions, once again meaning that it can transmit over both the 2.4 and 5 GHz bands, but when devices connect over the 2.4 band, they still only receive something like the 802.11n specification. But that does still provide for backward compatibility for devices using the 2.4 GHz band. Now, while 11AX can be used in any situation, some of the primary enhancements were built around the increasing demand for improved performance in very high-density public networks, such as in airports, and to facilitate improved performance for bandwidth-hungry applications that are becoming far more common, such as video conferencing and streaming, or in large modern apartment buildings or hotels with many smart devices in use as well. So lastly, if we look at the pros and cons for AX, on the plus side, further improvements in the transmission techniques provides for better range even when using the 5 GHz band. It supports dual band connectivity. It offers very high speeds while also improving efficiency, thus using less power. On the downside, at the time of this recording, it is still a nascent technology, meaning that some of its characteristics may yet to be fully defined, which also translates into fewer AX devices being currently available. But like all technological advances, particularly when it comes to wireless, it likely won't be long until AX becomes much more common. Ultimately, when it comes down to all of these standards, most environments, and of course most home users, will always want the latest and greatest, so to speak. But I should also mention that at least for home users, in many cases these days it's simply a function of what your internet service provider offers. So they may have more than one offering, of course, but you should always verify exactly which standard they're using at any given time to ensure that your devices will all be supported at the best possible service level. In this video, we will compare some of the wireless frequencies that are in use for wireless communications, particularly the 2.4 GHz range, 5 GHz, and most recently 6 GHz, but we'll come to that in just a little bit. Now, the primary issue with those different frequencies is compatibility. These are radio transmissions, and any two devices that need to communicate over radio must use the same communication channel. In other words, if I'm listening on the 2.4 GHz frequency, I will not be able to hear any transmissions that are using the 5 GHz frequency and vice versa. So you always have to be using the same core frequency. Now, with respect to the primary characteristics of those frequencies, it typically comes down to range and speed, and each implementation of wireless communication will have pros and cons in either one or both of those characteristics. So in terms of some of the factors that can affect the Wi-Fi range, clearly the distance from the access point is the primary consideration. And this, of course, applies to all radio communications. The farther away you are, the more difficult it is to pick up on a reliable and consistent signal. In addition, traveling through solid objects clearly will affect radio signals as well. So when you're talking about even something like your home Wi-Fi, the farther you are from it clearly makes a difference, but so do the amount of walls and or floors and ceilings between you and your wireless access point. And of course, this can be even more of a consideration if you're talking about something like an office building where there could be many floors and a lot of steel and concrete in between the 2 points. So in short, the fewer objects in the way, the better. And then, of course, the amount of power. This will determine how strong the signal is over longer distances. So if you have more power in the signal, this can help to overcome the problem of being too far from the access point. Now, Wi-Fi 6 is a standard that was introduced with 802.11ax, and this is a relatively new implementation of Wi-Fi at the time of this recording, but it is capable of running on either the 2.4 GHz band or the 5 GHz band. Now, I should clarify that, in fact, it can actually transmit on both at the same time, but any single device can only pick up on one of those signals. So if I'm sitting here with my laptop, I cannot connect to both the 2.4 GHz and the 5 GHz at the same time. But it offers better speed and range than either of the previous implementations simply due to more efficient use of the available bandwidth, while at the same time using a lower power consumption. So again, this is relatively new, but it is becoming more and more common. Now, another new standard is Wi-Fi 6E, which now actually runs on the 6 GHz band. This offers speed that is better than either of 2.4 or 5 GHz, but it is exclusive to Wi-Fi 6E devices. So this means that all of the devices you are using must all support Wi-Fi 6E. And it also offers twice as many transmission channels as the 5 GHz band, which itself had more channels than the 2.4 GHz band. So if we look at some of the characteristics with respect to range for just the 2.4 GHz and the 5 GHz bands for now, it does still depend on the standard for 802.11 transmissions, because again, like all technologies, things improve over time. So going back to some of the earlier implementations, such as 802.11a, this used the 5 GHz band and could carry, in actuality, around 195 feet, but could be tested in theoretical or perfect conditions to up to 390. But theoretical simply means that you were very unlikely to realize that value in practical implementations. 802.11b used the 2.4 GHz band and typically could carry around 230 feet. 802.11g also used 2.4 GHz and could only carry around 62 feet. 802.11n on the 2.4 GHz band could carry around 410 feet, and 802.11n on the 5 GHz band could carry around 230 feet. Then 802.11ac on the 5 GHz band up to 410 feet if amplified, but then 802.11ax using either the 2.4 or the 5 GHz band doesn't really have a specified distance limitation at this point. Now, to say that it's unknown isn't entirely accurate. There just hasn't been enough testing to come up with a consistent value. And the same thing applies to Wi-Fi 6E using the 6 GHz band. But what I can tell you is that the 6 GHz band, just by nature, will typically not carry as far as some of the lower frequency bands. Then if we also look at the speeds for each of those, Again, it depends on the implementation, but going back to some of the earlier ones, 802.11a on the 5 GHz band typically would achieve between 3 to 32 megabits per second. 802.11b on the 2.4 GHz band only around 2 to 3. Now again, I reiterate that these are the actual speeds, not the theoretical. 802.11g on 2.4 GHz, 10 to 29 megabits per second. 802.11n on 2.4, 150 megabits per second. 802.11n on 5 GHz, up to 450 megabits per second. 802.11ac on the 5 GHz band, 210 megabits per second, up to 1 gigabit per second. And 802.11ax on the 2.4 or the 5 GHz, somewhere in the neighborhood of 800 megabits per second. And then once again, Wi-Fi 6E using the 6 GHz band simply hasn't had enough testing to come up with a consistent value, but it is expected to be well into the gigabit per second range. Now, finishing up with some pros and cons for each band. For the 2.4 GHz band on the Pro side, it typically had greater coverage area than 5 GHz, and this is simply due to the nature of radio transmissions. Anything that is transmitted at a lower frequency tends to travel farther and penetrate better through obstacles such as walls and floors. But on the downside, it had a slower data rate, and it was also more susceptible to interference because there were a lot of other devices that also used 2.4 gigahertz. Now, this would depend on where you were and what you had, but some examples included cordless phones, and I'm not referring to smartphones in this case, rather a standard landline that you might have in your home, but cordless between the device itself and the receiver. They used 2.4 gigahertz, and some appliances in your home, such as microwave ovens, might also use the 2.4 gigahertz band, so they simply interfered with each other from time to time. For the 5 gigahertz band on the plus side, it typically had a higher data rate in almost all implementations, and it was less susceptible to interference simply because fewer devices used this band. But on the downside, it had a smaller coverage area, and it was less successful at penetrating solid objects, and again, this is simply due to the nature of radio transmissions. The higher the frequency, the shorter the distance, and the less able it is to penetrate obstacles. Then, as far as Wi-Fi 6 considerations are concerned, on the Pro side, it is backward compatible, meaning that it can operate on the earlier frequencies of 2.4 and 5 gigahertz, and its implementation of transmissions on the 5 gigahertz band actually do offer greater range than earlier implementations simply due to performance enhancements and improvements in the technology, and it also performs better at longer distances, while at the same time making more efficient use of the bandwidth and using less power. But on the downside, it is still a fairly new standard, so a lot of devices may need to be upgraded, which introduces the consideration of cost versus performance, because of course your physical infrastructure may need to be entirely upgraded to be able to use Wi-Fi 6. And finally, for Wi-Fi 6E on the Pro side, it does offer significantly higher data transfer rates than all of the predecessors, but it is designed to perform best indoors. Now, just hold that thought for just a moment. On the downside, it does have a shorter range, which comes back to the indoor performance, but there's more on that in just a moment. It does still use a shared 6 gigahertz spectrum, which comes back to the indoor performance. The idea behind the short range version is that it's designed to be used indoors, but there are other types of communications that were designed to communicate outdoors that have longer range. So that whole 6 gigahertz spectrum is shared between indoor applications and outdoor applications. So you need to be mindful of that. There can be some interference, and it does require dedicated hardware, which again could be costly in terms of upgrading the infrastructure, and there could also just be some confusion between Wi-Fi 6 and 6E. So if you're in a situation where you are considering an upgrade, then be sure to consider all of the specifications for each of these implementations to be sure that you are implementing the correct type. In this presentation, we'll take a look at another aspect of Wi-Fi communications, which is the channel. Now, very much like listening to the radio in your car, you need to tune it to the right channel to get your station. But with respect to Wi-Fi, we tend to be a little more general when we talk about the frequencies. Most notably, in almost all references to Wi-Fi, you'll likely hear the term 2.4 gigahertz. Now, we're going to talk about the 5 gigahertz band as well, but we'll come to that in just a moment. So, specifically, with respect to the 2.4 gigahertz band, another way to say that is 2400 megahertz. But in actuality, Wi-Fi transmissions using the 2.4 gigahertz band range from 2401 megahertz up to 2495 megahertz, with that entire range being divided up into 14 different channels. And depending on where you live, some of those channels may not be permitted for use over Wi-Fi because many countries implement restrictions over which communication channels can be used for certain types of communication. So the channels that are available to you may vary somewhat. Now, since the range of frequencies used goes from 2401 to 2495, and because there are 14 channels, a little bit of arithmetic would tell you that 2495 minus 2401 equals 94. Divided by 14 channels equals approximately 6.7. Okay? Now, before I go any further with this, I want to emphasize that this is not the way that channels are implemented, but stand by for just a moment. So, that math might lead you to believe that each channel covers a range of 6.7 megahertz, which is also a way of saying that the channel is 6.7 megahertz wide. But, as mentioned, that is not the case. In the 2.4 gigahertz band, in fact, each channel is over 20 megahertz wide, which subsequently requires that some of the channels overlap with each other, because if each channel is 20 megahertz and there are 14 of them, that is a lot more than 94. Now, that said, at the end of the day, as long as each device is set to use the same channel, then they will be able to communicate, but the overlapping channels can still lead to some interference. And I'll come back to that point in just a moment as well. But with the way they're laid out, so to speak, there are channels that don't overlap with each other, such as what we see here on our slide. And in particular, channels 1, 6, and 11 are far enough apart from each other that they don't overlap. Now, the same could be said for channels 2, 7, and 12, 3, 8, and 13, and 4, 9, and 14, but here in North America, 1, 6, and 11 are available to be used, and since channel 1 is the first option, it's almost always the factory default setting for most wireless access points, hence 6 and 11 become the other two channels that don't overlap. Now, as mentioned, depending on your region, some of those other channels may have been reserved for use by devices in various other industries, specifically what's referred to as the ISM sector, which means industrial, scientific, and medical. But again, 1, 6, and 11 are not specifically used in most regions, making them good candidate channels. So here we see the complete breakdown of the frequency range for each channel, but coming back to the issue of possible interference, as mentioned, it certainly is still possible, even for devices using different channels. For example, if your device is connected to its access point using channel 1, but your next door neighbor has their Wi-Fi set up to use channel 2, then those channels are overlapping and you could easily be in range of one another. But the interference would be negligible because the frequency refers to a wave pattern, and each wave has a low point, a high point, and a center point. So if, for example, you look at the center point for channel 1, it centers at 2412 megahertz, but channel 2 centers at 2417. Not much of a difference to you and me, but easily distinguishable for radio transmitters and receivers. So again, yes, sometimes interference can still happen, but it wouldn't be to the degree of not being able to establish connections to your devices at all. You just might not get optimal performance. But again, if you look at channels 1, 6, and 11, none of their values overlap at all. So these are simply the best options to avoid interference as much as possible. Now the same principle applies for the 5 gigahertz band. It's not just the 5 gigahertz frequency that's used, but there is in fact a wider variety of channels for the 5 gigahertz band. The channels begin at 36 and increment by 4 up to 56, but from that point it gets a little more random. We see channels 100, 120, 124, 132, 140, 157, 161, and 165. But in fact, this is not the complete list of the entire 5 gigahertz band. But again, none of the frequencies in use by those channels overlap with each other. Plus, the 5 gigahertz band is more regulated than the 2.4 gigahertz band is, which results in 2 distinct benefits. One being that there are simply fewer devices using these channels, which is why the 5 gigahertz band overall is less susceptible to interference. And the other being that because there are more distinct non-overlapping channels, the 5 gigahertz implementation of Wi-Fi actually allows for channels to be combined. Each block of 4 frequency ranges, for example between channels 36 and 40, is 20 megahertz wide. But by combining them, you can create channels that are 40, 80, and even 160 megahertz wide, which allows for the greater bandwidth that 5 gigahertz transmissions can support, while still allowing you to have dedicated frequency ranges for other standard or non-combined channels. That said, the regulations that are in place are still dependent on where you live. For example, in Europe, transmissions are overseen by the ETSI or ETSI, which is the European Telecommunications Standards Institute. In North America, typically it's the FCC or Federal Communications Commission, and Japan has their own governing body as well. As for the values that we see in the chart, indoors refers to the fact that the channel is reserved for devices that are primarily used indoors, such as Wi-Fi. DFS is dynamic frequency selection, which is simply a feature whereby communicating devices are able to negotiate the best channel. TPC is transmit power control, which refers to devices using as little power as possible to maintain the connection, and SRD refers to short-range devices. So again, how those channels are regulated varies depending on the governing body, but for the general population simply wanting to use Wi-Fi, this tighter regulation over the 5 gigahertz band ultimately translates into less interference. The specifications of indoors, DFS, TPC, and SRD are all applicable to what you and I consider to be standard Wi-Fi communications. Now, recall that these days many wireless access points support the use of both the 2.4 and the 5 GHz bands, in which case you simply have the option to configure the channels for each band. So just to recap, the optimal candidate channels for the 2.4 GHz band are 1, 6, and 11, because they're far enough apart that they don't overlap, and fewer non-Wi-Fi devices would be using these channels, so they're the least susceptible to interference. Then for the 5 GHz band, you will likely see some variance here with respect to your location, but it's likely that you would see channel options beginning at 36 and going as high as 165. Now, all of that said, I'd like to finish by saying that in either band, these days, and in fact going back several years, devices communicating over Wi-Fi have been able to auto-negotiate the optimal channel. And in most cases, this is the recommended approach, because the devices can quite literally determine for themselves which channel offers the best performance. So unless you have a specific reason to change this behavior, such as a known issue with a particular channel that you always want to avoid, In most cases, you should simply ensure that your devices are set to auto-negotiate. This is usually done within the graphic interface of the wireless router and in the settings of the wireless adapter on devices such as laptops, and it would almost certainly be the default setting as well. In this video, we'll examine some of the transmission characteristics of Bluetooth communications, beginning with the frequency, which does also operate in the 2.4 GHz frequency band, which is the same as many implementations of Wi-Fi. So it is possible that Bluetooth devices could interfere with Wi-Fi from time to time, but it's usually not much of an issue for a few reasons. For starters, the portion of the overall 2.4 GHz frequency band that Bluetooth uses has channels spread across 79 different independent frequencies, with each channel being only 1 MHz wide. Individual Wi-Fi channels in the 2.4 GHz band tend to cover around 20 or more megahertz. Due to that specificity, Bluetooth is less likely to cause interference. Plus, Bluetooth implements what's known as frequency hopping spectrum, meaning that transmissions quite literally jump around, so to speak. They can change from channel to channel quite randomly and quite rapidly, so the amount of time spent on any one channel is not very long. Finally, Bluetooth transmissions are simply much weaker than Wi-Fi, carrying only around 30 feet on average, so they just aren't strong enough to really cause any significant interference with Wi-Fi. Now, that all said, Bluetooth is a very useful and commonly used protocol which allows us to connect a wide variety of devices for increased functionality and ease of use, and the list of devices that can use Bluetooth is growing rapidly. On that note, there are some very common examples of devices that use Bluetooth these days, including smartphones and tablets, mice, keyboards, headsets, and speakers. And those are only a few examples. Others might include fitness monitors, GPS devices, smartwatches, and many more. But typically, when you are dealing with any two devices that need to communicate using Bluetooth, they must first be paired with each other. This allows each device to recognize the other and to ensure that any non-paired devices don't interfere with communications or even attempt to communicate. Plus, Bluetooth uses its own dedicated transmitters, receivers, and protocols, so it has no reliance on any other type of connectivity such as Wi-Fi. And while the practical range of most devices these days is still limited to around 30 feet, there are newer versions that have extended that to up to 100 meters, and in fact, the latest version has actually pushed that all the way to 400 meters, but it's unlikely that you would see these kind of distances in practice, at least at the time of this recording. That would be more of a theoretical test value. But like almost all communications technologies, improvements are continually being made. So then, in terms of pros and cons, on the plus side, Bluetooth itself doesn't really require much power, most notably due to the short range. So Bluetooth devices can usually run on battery for many hours before the battery drains. But of course, that's going to be dependent on the type of device and the primary functionality of that device. It does offer relative security with support for encryption and authentication being available. Plus, you can set any given device to not be discoverable, so that if attackers are eavesdropping or trying to pick up on stray signals in an attempt to connect to something like your smartphone, if the phone is set to not be discoverable, then it won't appear in the list of available devices on any other device. It's a very versatile protocol supporting many different types of communication, and again, the list of Bluetooth-enabled devices continues to grow, and it uses a very developer-friendly platform for manufacturers who want to create new Bluetooth-enabled devices. On the downside, there can be connection issues, but that's true of many types of wireless communication methods. That said, devices can be inconsistent during the pairing process. For example, you might be trying to pair two devices, but one does not recognize or see the other, which could be due to normal radio interference from other sources such as Wi-Fi or even some household appliances, or maybe there's an obstruction in the way, or perhaps other nearby Bluetooth devices are interfering with the pairing process. But for the most part, the convenience offered by Bluetooth greatly outweighs some of these drawbacks, particularly when compared to using wired connections for all of these devices, which may have offered more reliable connectivity, but it also required using a multitude of wires, which effectively negated the convenience of using Bluetooth in the first place. It's because it's wireless that we want to use it. In this video, we'll discuss what's known as long-range fixed wireless access, which is a method of providing wireless connectivity through radio links, as the name indicates, between two fixed points, such as building to building or site to site, which in turn enables data communications between those sites when the distance is simply too great for traditional Wi-Fi methods, and installing cables would simply be prohibitively expensive or just impractical. The transmission protocols use a point-to-point configuration, meaning that it's designed to be used only between those locations, as opposed to being able to be picked up and used by many locations. And typically they use terrestrial microwave, which means that there are dedicated antennas, so in other words, no satellites are required. Long-range fixed wireless tends to be a little more common in rural or remote areas where standard internet infrastructure isn't as common, so connectivity in at least one site could be shared with another site. For example, schools, libraries, medical facilities, or fire or police stations might share the connection of some kind of a primary location using these types of transmissions. Some considerations for implementing fixed wireless, however, would certainly include the geography with respect to what kind of distance you're dealing with and or the terrain between each location. For example, if there are many natural obstructions such as hills and forests, or of course artificial obstructions such as buildings, you may not be able to maintain reliable connectivity. Licensing refers to the frequency band being used, of which there are several unlicensed frequencies available, including 900 MHz, 1.8 GHz, 2.4 GHz, and 5 GHz, whereby unlicensed means that it's available to be used, and it shouldn't interfere with any other telecommunications providers or government agencies, but may suffer from or cause interference with other devices using those same frequencies, such as standard Wi-Fi. And the frequency that is used will actually be a function of the antenna you purchase or lease. They are, of course, larger and designed specifically for outdoor use, and typically focused to make the beam as narrow as possible. And they are also available using licensed frequency ranges that can be used to provide a better quality signal and cover longer distances, but of course, licensing requires that you pay to use that band. Another consideration of the antenna is the power output, which is typically very tightly regulated in most areas to ensure that they remain within safe transmission limits. But of course, the more power your antenna has, the farther it can transmit. But since most fixed wireless antennas aren't hundreds of feet in the air, you still have to remain within the regulated limits, which in North America anyway usually maxes out at around 1 watt. Now that might not sound like a lot, but as a reference, most cell phones transmit at only about 200 milliwatts, so that's 5 times less than a watt, and they can transmit several kilometers. So it wouldn't be uncommon for most point-to-point connections of long-range fixed wireless to be using comparable levels of power, because again, the beam is much more focused as opposed to a cell phone, which transmits much more broadly. Finishing up with some factors that can affect the performance of long-range fixed wireless. As mentioned, the geography between the two locations is likely the most common cause of interference. So the more open and flat the terrain, the better the signal quality. And of course, if you are using the 2.4 GHz band, there can certainly be interference from the multitude of other devices that use this band as well. But if you're in a remote or rural area, this might not be as much of an issue. And if the signal has to carry over any significant amount of water, what's known as tidal fading can occur, whereby the signal's own reflections off the water can interfere with itself. That all said, long-range fixed wireless can be a good solution for any organization that needs to connect remote locations when wired connections might not be feasible, so it's certainly worth consideration if such a scenario applies to you. In this video, we'll examine the characteristics of near-field communication, or NFC, and radio frequency identification, or RFID. So, beginning with NFC, this is a form of contactless communication that is commonly used in devices such as smartphones and tablets, whereby a user simply places each device in very close proximity to the other to exchange information, which in most applications will occur automatically, although you may receive some kind of a prompt to confirm the exchange depending on the application. Now, one of the most common implementations of this is payment. Most smartphones, for example, allow you to store payment card data in some kind of a wallet type of application. So to make a payment, you can simply use your phone instead of carrying around multiple payment cards. Now, that's only one example. Another common use of NFC might be to synchronize data between your phone and your tablet. Now, near-field communication is aptly named because its range is very limited. It's literally a matter of inches, so the communicating devices typically have to be almost in contact with each other to exchange information. But that feature itself helps to add a bit of extra security because the transmission range is so limited. It makes the exchange of data more difficult to be picked up on by someone who is attempting to eavesdrop on stray signals. So in terms of pros and cons, on the plus side, it's certainly very convenient and it's a seamless application. You typically don't have to do anything other than just store the appropriate information in your device. And it's supported by most major vendors, plus the communicating devices do not need to be paired with each other like they do in something like Bluetooth. As soon as they're within range of each other, the data exchange typically happens automatically. On the downside, in a corporate environment, it can be somewhat expensive for certain companies to adopt. For example, if you are considering an NFC-based application for inventory control or for security badges to allow access to your facility, you might have to purchase all new equipment, which could certainly be costly depending on the scale. And while the limited range does give you a certain amount of security, it's certainly not bulletproof. An attacker with an NFC-capable device could place their device close enough to yours without your knowledge, for example on a crowded bus or in an elevator, and they might be able to obtain personal information. This is typically where the confirmation might come into play to help prevent exactly this from happening, but it would depend on the make and model of the device and the application being used. Now, radio frequency identification, or RFID, uses an embedded chip and antenna to transmit and receive data, and it's a communication method commonly used for tracking, whether that be for vehicles, packages, pets, or even people. Anything with an RFID tag attached allows it to be identified if lost, and the data the chip contains allows it to be redirected appropriately. In terms of implementation, RFID belongs to a group of technologies referred to as Automatic Identification and Data Capture, or AIDC, which effectively means that all AIDC-based applications can automatically identify objects, gather data about them, and process that data automatically with little to no human intervention required. The primary components of any RFID-based application include the tag itself, which contains a built-in antenna, and a reader. The tags contain the desired information, which the reader receives, and it's then typically submitted to some kind of storage, such as a centralized database for processing. The tags themselves are often embedded into some other type of object or material, such as an ID badge, a fob, or any kind of credit-sized ID card, but they typically come in two forms, active and passive. Passive tags tend to be more common because they're smaller and less expensive to implement, but passive tags rely on being activated by the RFID reader before they can transmit data. Active tags, however, have a built-in power supply such as a small battery, which allows them to transmit data without relying on the reader. But of course, if they are self-powered, then this does introduce the possibility of that power supply being drained, in which case you would have to replace the battery, for example. Some common examples of RFID-based applications include asset tracking, inventory control, ID badges and secure facility access, fleet tracking, or personnel tracking. Lastly, looking at the pros and cons, on the plus side, RFID operates under a global standard, so it's maintained and operating specifications are updated regularly, which helps to ensure security and compliance. In many cases, a single tag can represent multiple items, such as all of the individual units in a single larger container, or the reader may be able to pick up on multiple tags at once, particularly if they're active tags, which can greatly speed up certain operations, such as processing a large shipment. And there is no line of sight required in most cases for the reader to be able to detect a tag. On the downside, there can be scanning issues, such as the ability to scan through certain materials, such as metal, and the multiple items feature just mentioned as a pro can sometimes be a con as well in what's known as a tag collision, which can occur if the reader is picking up on too many tags and is therefore not able to distinguish one tag from another. And there can still be security concerns, such as an unauthorized user reading or possibly even changing the data in a tag while a package is in transit, for example, perhaps altering the destination of the package. Ultimately, though, both NFC and RFID-based applications have led to many improvements in the way that devices can communicate, and many very convenient applications for us as users have arisen from both as well. Certainly always be mindful of the security concerns, but with a bit of due diligence, I'm sure you'll find that these methods of communication offer many benefits. In this presentation, we'll overview the Domain Name System, or DNS, which is a system that allows us as human beings to contact any given computer on the internet by using a familiar and easy to remember name. Now, I specifically say us as human beings in this context because ultimately the computers that are communicating require an IP address for internet communications, not a name. But we simply find it easier and more intuitive to use a name instead of trying to remember an address. So the name is really a layer, if you will, that we just overlay on top of the address. So it's the job of the DNS service to manage and maintain mappings that equate any given name to its associated address. Now, DNS arose because even in the earliest days of the networks that would ultimately evolve into the internet, it became quite clear that if we had to remember all of the IP addresses of every system on the network, we'd never be able to. So DNS was implemented using a hierarchical naming structure that makes it much easier for us to locate other systems. So in the example on our slide here, on the far right, we see a computer with the name of computer1.courses.skillsoft.com. This is what's known as its fully qualified domain name, or FQDN, but it is broken down into several parts, which represents the structure of the DNS hierarchy. Now, while in English we read names from left to right, the corresponding hierarchy is actually read from right to left. So again, in this example, the computer itself is simply named Computer 1, but then immediately to its left we see Courses. Then to the left of that we see Skillsoft, then Com, and then lastly a dot, which is used to represent what's known as the root domain, or quite literally the beginning of the hierarchy. So as we read the structure of the hierarchy from right to left, In fact, what's happening is that we're tracing our way back to the start, so to speak. Now, the reason for using this hierarchy is because these days there are so many systems on the internet that it would be impossible to create a single database that resides on a single server with the name to address mappings for every single computer on the internet. It just wouldn't be manageable or practical. Plus, that single server, if that was the case, would become immediately overwhelmed with all of the requests from client computers who need to resolve the names of the computers they're trying to reach. So the database is broken down and spread across many servers to balance the load. So it's referred to as a distributed database. So in terms of each component of the name, after the dot, which again is known as the root domain, we see several extensions that we're likely all familiar with on the internet, such as .com, .gov, .net, .edu, and .org. And each of these sections manage only that part of the name. So there would not be any actual name to IP address mappings at this point, but it significantly narrows down the options in terms of how you ultimately find the address you want. For instance, in our example of computer1.courses.skillsoft.com, we know that it ends with .com. So from the root, we know that we can just go to the .com section. Therefore, we don't need to follow the path of any of those other extensions. Hence, we've already eliminated a tremendous number of possible systems from our search. From that point, we move to the next level where we find the Skillsoft domain. And this is where things start to get much more specific, and it's also the point where the structure of the hierarchy is up to the business or the individual that owns that name. In other words, Skillsoft, in this example, owns the publicly registered domain name of skillsoft.com. So within that domain, they can create any kind of substructure that they choose. So we see the subdomain of courses. Now, that might only be one of many, but again, they can subdivide their primary domain however they like. So then finally, within the courses subdomain, there could still be several individual computers, but computer 1 is the one we're looking for. So by traversing the hierarchy, we're able to start at the root, which effectively represents every computer on the internet, and ultimately locate a single and specific system. So then, looking at the process itself, there are several components that are involved, and first of all, it begins with direction, if you will. The DNS database, as mentioned, contains mappings of names to IP addresses, but what that also means is that you can have what's called a forward DNS lookup and a reverse DNS lookup, because you are literally saying this name equals that IP address. So forward means that you know the name and you are trying to look up the IP address. Reverse is the exact opposite. It means that you know the IP address and you are trying to look up the name. Now, that's far less common, but sometimes it is the case. So then we make our requests to a particular database that stores the host address information, which resides on database servers. Now, from our perspective as users, our individual computers are configured with the address of a DNS server. So whenever we have to start looking, we contact that specific database server. It's part of your TCP/IP configuration. That server then begins the process of locating the name that we want to find. But ultimately, our individual client computers are the ones that will receive the mapping of this IP address equals that name. So that is then referred to as the DNS resolver. You have resolved the question, if you will. You have obtained the IP address for the name that you already knew. So again, all of that has to traverse that DNS server hierarchy to find it, but the hierarchy simply represents the logical structure so that you can traverse it efficiently to locate the very specific computer that you need to find. Some other key features again involve the resolver, as just mentioned. But something else that happens once the name is resolved is caching of that resolution. So if you contact your local name server to then go to the root server, then for example to the .com server, then to the Skillsoft.com server to ultimately locate something like Computer 1, that will all pass through our local name server, who will then pass the results to us. Now that we have that answer, that system will cache it locally so that if I have to contact the same system again, I don't have to go through that whole process. I can simply look in my own cache and I'll find it. This makes the process far more efficient because none of that resolution has to happen again. So the resolver will cache all results that come back. Now they won't stay in that cache forever because the name of a system could change, as could its IP address. But if it's in the cache, then again, none of this resolution process has to happen at all. You will simply see that it's in the cache and you'll contact that system directly without having to go through any of that iterative process. Some other components include the DNS servers themselves, and again, their job is quite simply to maintain the directory of domain names, which are subsequently translated to IP addresses. But again, recall that any given DNS server only holds the names for the portion of the hierarchy for which it is responsible. So again, going back to the Skillsoft example, there would be possibly still many servers within the Skillsoft domain that would handle the name resolution requests for their particular part of the domain. Recall that we saw the courses subdomain. Well, there could be many other subdomains, and if there are several of them, then each one of those portions would have their own servers to maintain that portion of the directory. It could just be a single server, but you can also have many servers if you want to for redundancy and fault tolerance. The DNS servers themselves have a structure that is essentially similar to a phone book in that there's an address and there's a name. And as mentioned, we will typically know the name, but we need to know the number. So if you've ever looked up a phone number in a phone book, it's the same process. You probably know the person's name, but you want to find their phone number. So DNS essentially works in the same way. But again, recall that it's a central registry, if you will, whereby all of the names are all available within that portion of the database. Then each portion is put together to create the entire hierarchy, but the entire hierarchy never resides on just a single server. When anything changes within that hierarchy, DNS does have to be updated. I just mentioned a moment ago that it is certainly possible for any given computer to have a new name or to have a new IP address assigned to it. If that happens, it is the responsibility of the client system to actually inform the database that a change has occurred. So, for example, even on your own local client computer in an office environment, if you get a different IP address, then your system will contact its pre-configured DNS server, and it will inform that server of the new IP address. Some other components include the DNS records, and that represents each individual address mapping. Now, that's not the only type of record, but that is by far the most common. So once again, that is simply the record that says this name equals this IP address, and that is also known as an A record for address. Now, TCP/IP has also implemented a new version referred to as IP version 6, which is much longer than the current version 4 address, but it's still the same type of record. It simply maps the version 6 address to a name, but to distinguish it from the A record, it's referred to as an AAAA record. A canonical name is also known as a C name, and it quite literally means an alias. It is possible for any given single IP address to be equated to multiple different names. For example, if you have webmail in your environment, you might open a browser and enter webmail.mycompany.com to get to the mail server. Someone else might think it's actually just called mail.myserver.com, but what you can do is set up canonical names so that both mail and webmail equal the same address. That way you still end up contacting the same server using two different names. Other records include the Mail Exchanger record, or MX, and these specifically indicate an email type of server. A name server, or an NS record, indicates any other DNS server that might be responsible for managing your portion of the DNS hierarchy. So what you can have is a primary name server, for example, and many other secondary name servers, but any name server within your DNS environment has an NS record. This allows any given client to be able to contact many different systems to resolve names. And if you do have those reverse lookups enabled within your environment, then you can create records that are specifically meant to service those types of requests. In order for that to work more efficiently, a PTR or pointer record can be created, which simply reverses the structure, and it says here's the entry in a reverse format. So ultimately, there are several benefits to DNS, most notably the ability for us to use easy-to-remember names. Again, it's just very difficult for us to remember a lot of numeric or alphanumeric addresses. And names are intuitive, so it just makes everything a lot easier. It's flexible and easy to use. Your computer, again, is responsible for informing its DNS server of any kind of change automatically, so we don't really have to do anything. All of it happens behind the scenes, if you will, and in terms of resolving addresses, all we do is usually open up something like a web browser and enter in the address. So again, it's very easy. There's a consistent naming structure. The hierarchy of the DNS is established, and all we have to do is sort of follow the rules, if you will. The servers themselves that maintain the database do implement security protocols to prevent intruders from doing what's called poisoning the DNS database, which essentially means that they would intentionally change either the name or the address or both, usually in an attempt to redirect you off to a malicious server, which might then attempt to ascertain private or personal information from you. And the database itself is very scalable and very fault tolerant. Once again, you can have as many servers as you want within your environment so that if one fails, there are other servers with the exact same records to satisfy client requests. So it becomes very fault tolerant in that manner. Because ultimately, DNS is a very required service these days. If you cannot contact a DNS server, you could still contact the system that you're trying to reach, but you would have to know the IP address. And in most cases, we simply don't. So by having a DNS server in place, it allows us to communicate quickly, easily, and efficiently. In this presentation, we'll take a look at the Dynamic Host Configuration Protocol, or DHCP, which is a means to implement IP address configuration as an alternative to static configuration through automatic addressing. In other words, if you are, let's say, a network administrator, all of the systems on your network need to have an IP address in order to communicate with each other using the TCP/IP protocol. So you essentially have two choices. You can manually visit each computer and manually enter an address, or you can implement DHCP, which will assign all addresses to all clients automatically. So clearly, doing it automatically is much more efficient, much faster, and easier, particularly if you are in a very large environment. Now, if you're in a smaller environment, let's say maybe 20 to 50 host systems, then manual configuration wouldn't really be a big deal. You could configure them all in maybe an hour or so. And that does give you the benefit of what's known as static addresses that won't ever change. Now, we'll talk about this more in a moment, but when you use automatic IP addressing, the addresses can change. That's why it's called dynamic host configuration protocol. So with static addresses, they don't ever change, but if you are manually entering the address across all of these systems, it's very easy to simply input an incorrect value, or possibly to input the same value on two systems, which would cause a conflict. So by using automatic addressing, you avoid a lot of these problems. And again, as mentioned, if you are in a very large environment, manual configuration really would just be too tedious and too time consuming and much too prone to errors. Now, with respect to the process, it involves your client computer, of course, and a server that is pre-configured with the addresses for the client systems to use. So what has to happen is that as your computer boots up, it issues what's known as a discover packet, which is effectively asking if there are any DHCP servers anywhere on the network. Any and all DHCP servers that are on the network will hear your request because the discover packet is a broadcast. In other words, everyone hears the discover request. So all servers will respond with offers. You will effectively hear those offers and you will request one of them. From that point, the server that issued that offer will acknowledge that you requested it, and it will enter it into the database that you asked for it, and it was acknowledged. At that point, you bind that address to your adapter. So at this point, everything is complete. So I should actually mention that all four of these steps are actually broadcasts, because your client will not officially bind that address to its adapter until you receive the acknowledgement. So it's a little bit of a noisy process, if you will, but once you get the acknowledgement, everything can settle down, for lack of a better word, and you can stop broadcasting. Now, there are other components involved, so let's take a closer look at that, if you will. Again, as mentioned, everything begins with the DHCP discover on the client, and I did say that a DHCP server will respond, but I also mentioned that it could be any one of several servers. Now, that's not to suggest that you have to have multiple servers. Rather, it just means that you can, because if you only have one DHCP server and it goes down, then a lot of clients might not be able to obtain an IP address. So you can have redundant servers to provide fault tolerance. Now, on any given server, there is what's known as a DHCP scope, which represents the pool of available addresses that particular server is able to hand out, the subnet mask, which needs to be used for your particular portion of the network, and various other options that you might also need as a client, most notably a DNS server. So it can assign all of that to you. DHCP reservations can also be configured so that if you have certain clients on the network that should always have the same address, they will get the same address. This effectively equates to manual configuration because that would be a static address, but it can still be handed out automatically. Again, the DHCP request is your particular client system saying, I would like to use that configuration. And the reason why I'm mentioning this again is because once you receive your IP address configuration from a DHCP server, requests actually happen again later on, and this is because every DHCP address assignment that you receive has what's known as a DHCP lease, which represents the amount of time for which that address configuration is valid. So let's say it's 10 days. At 50% lease duration, 5 days in this case, another DHCP request will actually be sent back to the same server that issued you that address configuration, and you'll essentially just say, can I keep using this address? And as long as the server goes through the database and verifies that everything still seems to be valid with the configuration, the server will say yes, you can keep using it, and your lease will renew at that point, giving you another 10 days. So once again, when you hit the 50% mark, the same process will happen. So in theory, if your client never turned off and the server never turned off, and there were never any disruptions to the network itself, you could keep the same address, again theoretically, forever. Now, with respect to the scope itself, as mentioned, this represents the valid range of IP addresses, and it's really up to you as an administrator to determine how many addresses are in that range. You have a lot of flexibility. You could create fairly small ranges if you need to be specific, or they could be very large. But the scope itself is simply something that you configure on the server, but any given server could also have multiple scopes configured so that it can service a wider array of clients, and they can also be configured from the perspective of security. In other words, you can specify various conditions that, if met, will allow you access to the network, and if not met, could deny you access to the network. Now, a few other points about the DHCP reservations. As mentioned, it is a permanent assignment that is always issued to the same specific DHCP client, and there are many types of DHCP-enabled devices that do support reservations. But in order for the reservation to work and to be assigned to the correct client device, you need to know its MAC address, or Media Access Control, because that is the only truly unique value when it comes to addressing. Every device on every network will have a MAC address if it has any kind of network interface, and they are all unique. So again, what happens is the client still boots up and still requests an IP address, but the server is able to ascertain the MAC address of any client because it's included within the packet information. So when the server sees that MAC address, it can just check its database to determine if that MAC address has been assigned to a reservation, and if so, it will always assign the same address to that particular client. Now, whether or not you need reservations is going to depend on the environment, but let's just say you have a particular system that is always used as a print server. As such, you always want it to have the same IP address so that clients always contact the same server. In that event, you can set up a reservation so that particular system always receives the same address, and that just makes things a little more consistent for your environment. But reservations are entirely up to you. Lastly, DHCP snooping is a security feature, and this comes back to the fact that the process of requesting an IP address is all done through broadcasts. Every system on the network hears broadcasts, so it opens up the possibility for an intruder to introduce an unauthorized DHCP server. In other words, let's just say I'm visiting your environment and I'm in a meeting room. I could create a DHCP scope on my system and fire it up and start handing out addresses to clients on your network as long as I have physical connectivity to that network. So this might allow me to redirect systems to malicious servers or untrusted websites. So DHCP snooping essentially implements a trusted DHCP response before the client will accept the response from that client. The unauthorized DHCP server would not issue any kind of trusted response. So your client boots up as per normal, it requests an IP address, both the authorized and the unauthorized server would hear those requests, and both of them would make offers. But the client would see that one of them is from a trusted server and one of them is from an untrusted server. It therefore will quite simply ignore the untrusted response. Ultimately, though, DHCP is one of the most common network services, and as long as your pools on the servers are configured correctly, and as long as you've taken security into account, then your client systems should absolutely receive correct and valid IP address configurations automatically, alleviating a tremendous amount of administrative overhead as compared to manually configuring every client system. In this presentation, we'll examine several different types of servers that are commonly implemented in a networking environment and even in the home environment. And these different types of servers are also referred to as server roles. Now, before we get into each role specifically, I'd like to also point out that roles can be implemented in either a dedicated or a shared manner. In other words, any given server can be dedicated to a role, particularly if that role is rather demanding, or any given server can have multiple roles. It generally comes down to the resources available on that server, and security is also a common consideration. For instance, if a role such as a print server offers fairly unrestricted access, while another role such as a mail server is very tightly controlled, then it might be a good idea to place those roles on separate or dedicated servers. In any case, the placement of roles is really up to you. So that said, beginning with the web server, this is a classic model of client-server computing, which refers to a client system, such as a person using something like a desktop computer or a laptop or even a mobile device, requesting access to the resources that reside on the server. Typically, you as the client would open up something like a browser and enter an address, which subsequently requests the web page from the server. The server then locates the requested content and delivers it back to you. That's client-server computing. So for web servers, this is done primarily by using the Hypertext Transfer Protocol, or HTTP, which is designed specifically to request and deliver web-based content over the internet. And you have likely noticed that sometimes when you open a browser and visit a site, the first part of the address often says http://, which indicates that this is the protocol being used, and for all intents and purposes, it is the protocol of the internet. Now, the web server itself is typically a dedicated system because it does have to be exposed to the internet, so it generally does not run any other services other than what is minimally necessary. There might be other protocols, such as the File Transfer Protocol, or FTP, for developers to upload content to the web server, but it's usually in a fairly dedicated configuration. Again, in other words, the web server does not really do anything else other than perform web services. Now, the platform that you will typically find on a web server, in other words, the software that manages all of this, is probably one of either Apache, Internet Information Services, or IIS, or NGINX, which is actually pronounced Nginx. Now, Apache is very commonly used. It's an open source platform that typically runs on Unix or Linux systems. IIS is a Microsoft proprietary platform, and Nginx is also open source and runs on just about any operating system. In all cases, the platform simply allows you to manage the content for any given site, and there can be any number of distinct sites on any given web server. Again, it really just comes down to how robust that server is. And of course, you can control and manage access to those sites using their features. In terms of considerations with respect to which platform you should implement, it will generally come down to compatibility. In other words, will it work well with the other servers and operating systems in your organization? And are there any limitations on what kind of clients it will support? The level of security required is certainly a major factor. For example, will it deliver unsecured websites, or will it also host secured sites, or possibly even both? And of course, what kind of built-in tools are available for publishing and managing the sites on an ongoing basis, and possibly what kind of third-party or other tools might also be supported by that platform. Now, file servers would actually be similar to web servers in terms of functionality because, again, file servers are also classic examples of the client-server model, because the client simply requests a document and the server returns that document, and the server itself is responsible for the central storage and management of all of the files in your environment, which might include documents, images, spreadsheets or reports, presentations, or any kind of content that is typically used in a network environment. But unlike a web server, the files are accessed by client computers on the same internal network as opposed to over the internet. So there typically wouldn't be any kind of external access to file servers. Plus, web servers are essentially dedicated to web-based content, whereas a file server can store just about any type of content. And in most cases, the protocol used to request files is known as SMB, or Server Message Block, which is a protocol supported by several platforms, including Microsoft and Linux Samba. In fact, the name Samba is derived from the letters SMB. As mentioned earlier, any type of server can be either dedicated or non-dedicated, or shared if you will, and file servers in particular really don't have any set rules in that regard. It is up to you, but in terms of making that decision, dedicated servers will generally provide faster data access and offer more storage capacity, which might be more important in very large environments where demands are high. Conversely, smaller environments with lower demands may find that a file server isn't under much stress at all, so it is therefore available to perform other roles, which can help to reduce costs and administrative effort by not requiring another server. Again, really, it's your call. Print servers, as their name indicates, are used to manage print requests from other users. Now, to clarify, any standard computer can have a local printer attached to it, which of course will service your own print requests. But to be classified as a print server, it has to be servicing the requests of other users on the network. Just like folders on a print server can be shared with other users, so can printers. So once you have a printer locally installed on a server in your network, you can then share it, and other users will see it as available to be installed remotely on their own systems. Once they do so, they can begin to submit jobs to that network printer so that they don't need their own local printer. If many users have installed the network printer, then each user can just double-click on the icon that represents the printer, and it will show the status of the queue, which not only shows users the status of their own print jobs, but all other jobs that might be waiting to be processed. Typically, standard print users can delete, pause, or resubmit their own print jobs, but they can't manage the print jobs of other people. Although you can set up specific print server administrators who would have that ability. For example, if I only needed to print a single-page memo, but I see that a very large job, such as a lengthy article, is ahead of my job in the queue, I could ask a print administrator to move my job ahead of the very large job. Now, that kind of implementation might be common in a large enterprise network, but just like the file server, print servers can be set up in small offices or home networks as well. In fact, even most desktop platforms will allow you to share a printer with other users once it has been installed. So, coming back to the home file server we just talked about, if a printer is installed on that same system, it could also be shared, and all other users could connect to it and submit jobs to that single printer, so that you don't have to buy a printer for each user in your home. Nor would they have to transfer their files manually to the desktop acting as the server to be able to print them. They simply install that same printer as a network printer on their own devices and submit their print jobs from those local devices. Just like file servers, print servers can be dedicated, particularly if you're in a very demanding printing environment such as a print shop. But I will say that for most business environments, printing tends to not be all that demanding, but it does depend. So it's not uncommon to see print servers combined with file servers. Again, that's your call. But in fact, on Microsoft operating systems going back to the days of Windows 95 and 98, the service to install, which allowed desktop systems to share their files and printers, was actually called File and Print Sharing. Now that simply indicated that it was the same service used to enable sharing of both of these types of resources. But again, that's just a common implementation. How you set up your file and print servers is your call, but those two roles are commonly implemented on the same server. Network devices can also manage and control access to printers, which is probably more commonly implemented in smaller offices or home networks by sharing the printer through something like your internet router. Most routers at that level had network interfaces so that you could connect your printer directly to the router, then enable and configure shared access through the interface of the router. Once configured, anyone who was connected to the router would be able to print as well. This was a good alternative to setting up something like a dedicated desktop to act as the print server, because if you did that, the system hosting the printer always had to be on to accept print jobs. And if it was just a desktop computer in the house, for example, then it could be turned off quite often. But the router is likely never turned off. So this made things a little more convenient. And on that topic, as mentioned, just about any client computer these days likely also has the ability to act as a print server, but it's not something that is usually available by default. In other words, the feature itself has to be enabled on the desktop system, then the printer itself has to be set into a sharing mode. If you're running Windows computers on your home network, most of this can be done by running the home group or the home networking wizard. But once you do so, the other systems on your network will be able to submit print jobs through the host computer. In short, your computer does not have to be some kind of official server-level operating system to be able to act as a print server. Now that all said, I should also mention that these days, many printers have their own print server capabilities built in. In fact, I'd say that it's likely that many of you have a printer right now that simply connects to your Wi-Fi network just like any other device. Then the printer itself is available over Wi-Fi. So anyone on the same Wi-Fi network would be able to submit jobs to that printer without the job having to be processed through any other computer or device. Again, the printer itself is the print server. But this type of configuration would in fact be something that is much more applicable to home or small office environments. In large corporate networks, administrators would almost certainly not want their printers to be accessible over Wi-Fi simply for security reasons, although there might be some localized exceptions, such as a printer in a boardroom or maybe in a common area. Finally, mail servers provide what is perhaps the most important service for any environment these days: email communications. Now, there are many different ways by which email can be handled, especially these days with the prevalence of cloud services, and an email server, unlike a file server or a print server or maybe even a web server, is something that you would almost never see in a home environment. That's not to say it's impossible. If, for example, you run a business out of your home, you might have your own mail server, but they are almost always exclusively found in corporate environments. Now, not only do they provide email functionality, but also calendar services such as booking appointments and meetings, storing contacts, notes, reminders, tasks or to-do lists, and several other services. Regardless of the services provided, though, the implementation of a mail server allows for all mail for all users to be centralized on that server. And of course, many servers can be implemented for fault tolerance and load balancing, but this removes the requirement for any mail to be stored locally on any given device. With this type of implementation, it doesn't matter which personal device you use, such as your desktop, your laptop, or your mobile phone. You are always simply accessing your mailbox that resides on the server, so any device can be used. In addition, many environments will also make user mailboxes accessible from the internet through either a VPN connection or through webmail, which allows for access anywhere, anytime, as long as you have an internet connection. Now, there are many platforms available for mail servers, but some common examples include Microsoft Exchange for those running Windows, which most commonly uses Microsoft Outlook as the mail client, IBM, Lotus, and Domino. Domino is the server component and Notes is the client. And then, quite literally, there are too many open source platforms to list, but these would most commonly be implemented in a Unix or a Linux environment. So, of all of these server types, it simply comes down to which services you need, and then how you want to implement each one. And on that note, I'd like to quickly come back to the idea of dedicated versus shared server roles. With respect to mail servers, this is an example of a role that is almost always dedicated, especially in larger environments. Processing and storing the mail for all users within a large network can be a very demanding task. Plus, mail servers almost always need much more robust security, so it is very commonly implemented as a dedicated role. In this video, we'll take a look at what's known as syslog, which is a protocol that enables network devices to send messages and status information to a centralized logging server. For example, a network appliance such as a switch may send event messages informing the syslog server that one of its ports has lost connectivity. Many network devices these days support the use of syslog, which in turn allows for very robust monitoring applications to be built that allow you to gather information across your entire network so that you don't have to physically go from device to device to examine the logs of each one to get a picture of what's been happening on your network. Syslog is also supported on most major operating systems, including Unix and Linux, Mac OS, and Windows, although Windows-based servers do not support syslog natively, meaning that they require a third-party tool to collect the information on target systems, which is then forwarded to the syslog server. That said, I do want to point out that Windows-based Active Directory servers do have a folder called syslog, but it's not used in the context of this topic. Active Directory domain controllers use the syslog folder to replicate files to and from each other, such as configuration policies, so that all domain controllers will have identical copies of those files. So that's a different process. And I'd also like to point out that Windows-based servers also support the collection of event logs from other servers or even clients on the same network, so that you can gather the logs from many other computers to a centralized server. So this is certainly very similar to the topic at hand, but it's specifically for what's known as the event logs on Windows-based systems, and in fact this process is called event log forwarding. So devices such as routers or switches can't participate. In terms of the process, the network devices that are configured to report to the syslog server will effectively keep track of what's been going on within themselves. For example, they know when a user tries to access a specific port on a firewall, or when a request comes in to update a routing table, or which user submitted a print job that got stuck in the queue. In short, they all have their own internal logs. So the messages containing those log entries are simply sent to the syslog server, which acts as a central repository for all logs that are being gathered. From there, administrators can monitor or troubleshoot the devices if necessary, and notifications can also be configured so that administration is alerted when a particular event of interest occurs, such as an unauthorized attempt to gain access to a resource of some type. Now, one other point I should mention is that syslog messages are only ever sent from the devices to the server. In other words, the servers do not have any means to poll the devices, so all client devices have to be configured to report to the server, which is usually done on a scheduled basis. In terms of content, any given syslog message will typically include a timestamp, a severity rating, the device ID including the IP address from which the message originated, and other information specific to the event. For example, in the case of the stalled or failed print job that I mentioned, the message would include the user ID who submitted the job. With respect to the format, syslog messages are sent using UDP, or the User Datagram Protocol, over port 514, which translates into ensuring that if there are any firewalls in use between the device and the syslog server, this port will have to be allowed. And in most cases, the syslog messages themselves are in a human-readable format such as plain text, but that will depend on the device and the platform being used. And coming back to the severity level mentioned a moment ago, there is also a numeric value to indicate how severe the issue is, typically ranging from 0 to 7. And it might seem a little counterintuitive, but the lower the number, the higher the severity. In other words, 0 would indicate an emergency situation such as a complete failure of some kind, whereas 6 or 7 would only be for informational messages or debugging purposes. A typical syslog implementation uses 3 components: the syslog listener, which is configured on the central server to quite literally listen for the incoming messages from the client devices; the database, which stores all of these messages and allows for fast and easy searching so that you can locate any particular message of interest; and of course, management software that allows you to configure what information you want to gather and to configure alerts and notifications with respect to what will trigger an alert or a notification and who should be informed. Some other considerations when using syslog include the data management aspect, which refers to the fact that you might be dealing with a lot of information, particularly in very large environments, with a lot of devices submitting messages possibly all day, every day. So a syslog server needs a large database and, as just mentioned, an effective means to manage that volume of data with respect to filtering out the data that is most relevant to you. It should also be noted that syslog is not the same as simple network management protocol implementations, which is another protocol for network device monitoring, but SNMP operates in almost the reverse manner to syslog, because SNMP gathers most of its information by polling devices. Recall that syslog servers only listen for incoming messages. The devices aren't polled or queried. That said, SNMP data can be configured in what's known as an SNMP trap, whereby it can gather and send data without being polled. In that event, SNMP messages can be accepted by a syslog server. Just be mindful of what is being used in your environment, and even if you are supporting only syslog, there are also different versions including syslog NG and rsyslog. So to enable full functionality and compatibility, you should ensure that all devices are using the same version. That all said, advantages of syslog include being able to monitor many different types of events from many different types of devices, which simply translates into being able to maintain a much more extensive and comprehensive view of what is happening on your network. Without syslog, if something goes wrong, it could take significantly longer to even realize that something happened, and it can be much harder for your troubleshooters to trace and correct. In this video, we'll discuss a security framework known as AAA, sometimes referred to as AAA, which refers to authentication, authorization, and accounting. Now, we'll examine each one in detail in just a moment, but I'd like to quickly point out that the term accounting in this context refers to accountability, or being able to hold someone accountable for their actions, not the financial type of accounting. So, beginning with authentication, this is the process of determining that someone or something is true, genuine, or valid. More simply stated, it's the process of identification, along with the means to verify that identification. Now, we all do this every day, whether you're in an enterprise network or just sitting around at home. Each time you log into your online banking or your favorite webmail service or an online retailer, or in many cases just picking up your smartphone, you have to present some kind of identity and some way to confirm that identity, which is done most commonly by providing a username and a password. The username should be unique to you, such as an email address, which itself states who you are. But to then prove that you are who you are, a password is entered that hopefully is known only by you. From that point, the system or device to which you are attempting to gain access can compare the information you've provided against what has been previously stored in a secure database, and if values match, you're granted access, meaning that you have successfully been authenticated. If the values don't match, your access attempt is denied. Now, these days, security has become much more of a concern, and many different ways of verifying your identity have emerged. So, while a password is still perhaps the most commonly used method of authentication, some environments might require more than the password. And in any situation where more than one method of verification is required, this is referred to as multi-factor authentication. Since more than one method is used, it's simply more secure. For example, there are many ways that skilled attackers can gain access to your username and password, including very simple processes such as shoulder surfing, whereby the attacker discreetly watches you while you enter your credentials. So if that's all they require, then they might run off to their own computer and attempt to log in using the stolen credentials. But if the logon process then also requires the user to enter a code that was just sent to the legitimate user's mobile phone, the attacker would have no means to access that code, hence the login attempt would be denied, and the security of the authentication process is enhanced. Some other common methods of multi-factor authentication might include using a security token such as a card, a fob, or a badge with an embedded RFID chip, a biometric verification such as an iris or a retinal scanner, or fingerprint readers or facial recognition, or being prompted to answer security questions to which only you should know the answer. And of course, being sent the code that I just mentioned is also becoming very common these days. As long as any two of these methods of verification are being used, it is considered to be multi-factor authentication, and it is inherently more secure than single-factor authentication. An authentication server is the entity that is responsible for examining the credentials you've supplied and comparing them against what is stored in a secure database to determine if the credentials are valid. If they are, then the server provides you with some kind of software-based access token, which you use. You need to gain access to a resource such as your email, a shared document, the corporate database, a printer, or any other resource on the network. Now, this all happens transparently in the background, but each time you request access to a resource such as a file, the server that hosts that resource, for example, a file server, will ask you to present your access token. It will examine the identity in that token, which will then determine if you are allowed access to that file. The access token itself is typically valid until you log off, or until it reaches an expiry time as designated by an administrator, but then once you log in again, let's say the next day, the whole process occurs again. If you're familiar with working in a Windows Active Directory environment, the authentication server is known as the domain controller, but that's only one common example. There are many other types of services and even devices that can provide authentication, and it could be any kind of server dedicated to verifying identities. For example, if you have a more advanced security implementation in your environment, such as retinal scanners to gain access to secure rooms, then there would likely be a dedicated server that stores the retinal patterns of all users who have access. Ethernet switches, wireless access points, or any other kind of network access server such as a VPN server can all authenticate your request, which can be based on a number of different characteristics before they grant you access to the network they protect. An Ethernet switch, for example, might need to see a specific MAC address. If your address doesn't match any in the list of allowed addresses, your access through that switch is denied, which could prevent someone from using their personal device, such as their laptop, to connect to the corporate network. An access point, such as a Wi-Fi router, would likely require a password to connect, but could also use MAC address restrictions for tighter security, and a network access server is typically used for gaining access to the corporate network over a VPN, usually for when users are traveling or working from home. They would almost certainly require a username and a password as well. Even for purely home-based users, you likely authenticate to your devices all the time, such as by entering a passcode on your mobile phone or by using a fingerprint reader or facial recognition. Now, in day-to-day conversation, you might hear the terms authentication and authorization used somewhat interchangeably, and for the most part that won't cause any issues. But in terms of official context, and of course for exam preparation, they are separate and distinct processes. Most notably, authorization only ever occurs after authentication. In other words, you can never be authorized until you are authenticated. Authentication itself ends with the establishment of your identity. That's it. You've proven who you are. So now that your identity is known, authorization is the process of determining what you are allowed to do, what kind of access you have to resources, which operations you're allowed to perform, or even where you can go, for instance in a physically secure area such as a military base. So a moment ago I mentioned how you can gain access to a file on a server, but in order to do that, the authentication server must issue you your access token. There's that keyword of access. But the access token itself does not contain a list of your abilities. It only contains your identity and, if applicable, a list of groups or roles to which you belong. And I'll come back to that in a moment, but the groups to which you belong is a component of your identity. The list then of who is able to access any given file resides on the server that hosts that file in what's known as an access control list. So again, in order for the file server to determine if you're allowed to access the file as per the permissions in the access control list, it must know who you are. Therefore, authentication must always happen first. In entirely non-technical terms, if someone knocks on your door and if you ask, "Who is it?" and they provide a name, you could perhaps look through a peephole to verify. That's authentication. Whether you then decide to let them in is of course up to you, but if you do, that's authorization. Now, authorization can be implemented and enforced in a variety of ways, including the use of policies, which are typically implemented when the same set of abilities is applicable to many users. This way, a single policy can establish consistent settings to everyone affected by the policy. A common example might be that only administrators or tech support users are allowed to install software on user devices. This helps to prevent standard users from installing software that could be malicious or is simply unwanted in the environment. So once a user is authenticated, and as I mentioned a moment ago, once the roles and groups to which that user belongs is determined, if that user is identified as belonging to, let's say, the tech support group, they can install software. If they're identified as being part of the standard users group, they can't. Now, of course, that's great for when you need to apply the same type of access to many people at once, but there will always be instances where specific individuals will require specific permissions. So they can also be applied individually for more granular control. And of course, the level of access or the permissions that are available can vary significantly depending on the resource, the user, or the activity. But simply put, if authentication can be thought of as "who are you?", then authorization can be thought of as "what can you do?". Finally, accounting is the last component of the AAA framework, and as mentioned, it refers to accountability, which in this context means that access to resources and user activities can be monitored, and what the user does during any given session can be logged. This allows administrators and auditors to verify the actions that have taken place and the identities of the users who perform those actions to simply verify that you haven't missed anything, or to attempt to trace activities in the event of some kind of security breach. For example, in a very large environment, it can simply be difficult to know if you've checked every box, so to speak, when it comes to something like controlling access to resources. So by examining the logs, you might discover that certain users are able to access resources that they shouldn't be able to. Or if a malicious user does gain access to confidential information, characteristics such as the date, the time, the computer they were using, and of course the user identity that they used would all be contained within the security logs, so you could hold that user accountable. That said, accounting doesn't always refer to security issues. It can be used for billing purposes. For example, if you have a cloud subscription, the services you use and the resources you create are all tracked so that an accurate bill can be sent. Perhaps you want to analyze which users are using particular services most often and under what conditions, or maybe examine its use by demographics. You might also want to monitor and control the authorization process itself. For instance, if another administrator makes a change to an existing authorization policy that itself should not be allowed, you would want to know about it. And it might simply be to gather data as to how things generally occur in your current environment to help plan for changes in the future. Regardless of how you implement each component of the AAA framework, they all work together to allow any environment to effectively manage and control the daily activities of all users in a centralized and efficient manner. In this presentation, we'll examine several appliances and devices that can be used to help enhance the security of your networking environment, beginning with what's known as Unified Threat Management, or UTM. The term unified effectively means that it combines multiple security features in a single appliance, including network gateways with anti-spyware or antivirus, VPN servers, firewalls, email and anti-spam filtering servers, proxy servers, quality of service and bandwidth management servers, routers, and web security services such as managing certificates and providing encryption. So, given all of those potential services, it can be rather difficult to manage all of them, so a UTM gives you the ability to control and manage consistent settings across all of those services on a single device. Now, the services available on any given UTM appliance will vary depending on the make and model, but looking at a few examples of some fairly standard services, you might find a firewall, which can report which types of requests were blocked and which were allowed, perhaps a proxy server, which can specify the sites that were blocked and which ones were allowed, and we'll talk more about proxy servers later. An antivirus and/or anti-spam service can report on any identified malware and maybe any quarantine files, and a content filter could report on which type of information was blocked in web traffic or email because it matched various definitions such as the IP address or a list of keywords. Regardless of the specific services though, the UTM allows for centralized management of all of these, again within the single device. The next type of protection service is what's known as an IDS, or an intrusion detection system, which does exactly as its name indicates by monitoring network traffic for malicious activity. Now that said, what is defined as malicious in and of itself can be difficult to determine, so most IDS devices monitor for what is considered to be out of the ordinary. So in other words, they quite literally learn what the normal traffic tends to look like. Then if and/or when something is identified which is out of the ordinary, then that is considered to at least be questionable, and an administrator can investigate further. Now, there are two primary configurations for an intrusion detection system, a network-based and a host-based, respectively referred to as NIDS and HIDS. A network-based IDS is usually a dedicated device configured on the perimeter of your network, and everything behind it is protected, whereas a host-based IDS is a software application running on a specific computer. The overall level of protection on a host-based IDS certainly wouldn't be as broad as the network-based, but it's a good idea to have both, the network-based providing overall protection for the whole network, and the host-based providing extra protection for specific systems that require additional security. Similar to the IDS is the intrusion prevention system, or IPS, which goes a level beyond the IDS, if you will, by actively attempting to block suspicious traffic before it even enters your network. You may have noticed that for an IDS, the keyword is detection, whereas with an IPS, the keyword is prevention. So it might seem obvious to say that prevention is better than detection, and in reality, most devices will provide both services, But there are situations where you want to allow suspicious activity. If, for example, you're trying to determine who is doing what and in what manner. If you immediately block the traffic, then any kind of information about it is much harder to ascertain. If, for example, you suspect that someone is attempting to intrude into your network, you can set up what's referred to as a honeypot, which is effectively a decoy. It's presented as a trap, for lack of a better word, so the IDS will detect and log the details of the attack, possibly providing you with the information necessary to take legal action, or at the very least enough information to ensure that you can appropriately configure a block to prevent it in the future. That said, in many cases, network security administrators are already aware of many existing types of attacks or intrusions, so the IPS can be proactively configured to provide network security and threat protection by both detecting known vulnerability exploits and, of course, blocking them as soon as they've been detected. In short, detection is simply the process of monitoring and identifying suspicious activity, while prevention is the process of taking action. Another commonly used appliance is the load balancer, which does exactly as its name indicates as well. It distributes traffic evenly across several host systems that all provide the same service. For example, a single web server may easily become overwhelmed with client requests if it's hosting a very busy site. So multiple copies of the same site can be created on multiple servers. Then they can all be placed behind the load balancer. Client requests initially arrive at the load balancer, then it distributes those requests as evenly as possible to all hosts behind it. This can greatly increase the capacity of the service because many host systems can be placed in the collection or the pool of servers as they're commonly known, which subsequently decreases the burden on any one server, and they can greatly improve the reliability of the service as well because if any given host should fail, the load balancer can adjust dynamically and simply redistribute client requests across the surviving hosts. So this is simply a representation of what that configuration looks like. At the top we have client systems of any and all types making requests for something like a website, although I should mention that it can be any kind of service such as email, database access, or file services. So the load balancer is configured with what's known as a virtual IP address, which is simply a single address that is presented to all of the client systems because they have all made their request using a single DNS name, which would resolve to a single IP address, so all client requests will arrive on the load balancer interface, as opposed to the interface of a specific host behind the load balancer. And again, that collection of servers is referred to as the pool. You may also hear the term array, but in any given pool, there can be any number of hosts. And again, the load balancer will then simply distribute all requests across all pool members to avoid any one host becoming overwhelmed with requests, while another is hardly servicing any. Now, load balancers can be categorized into two layers, which refers to the numbered layers of the OSI model. So it can be performed at either layer 4, which is the transport layer, or layer 7, which is the application layer. Layer 4 distributes traffic based on the transport layer protocols such as TCP and UDP. Layer 7 distributes traffic based on the application layer protocols such as HTTP, FTP, SMTP, DNS, DHCP, and many others. In other words, layer 4 load balancing is not aware of the specific application being used, whereas layer 7 load balancers are. Layer 7 tends to be more common in most implementations because they're aware of these separate and distinct applications, and of course any one server might provide several of these services. Plus, layer 7 load balancers can monitor the health of any given service and redirect requests for just a failed service. For example, on a server that provides both DNS and DHCP, the server itself may be healthy overall, but one of those services may have failed. So it can continue to service requests for the running service, but the requests for the failed service will be directed to other hosts. Next, we have proxy servers, which are systems that will access some kind of service on behalf of a client, which is essentially what the term proxy means. Quite literally, it means I'll do that for you. Proxy servers can be used for content caching, filtering, and enhanced security for internet access. In terms of the configuration, the proxy server is placed between the enterprise network and the internet, or even an intranet, and it has what's known as a content engine to facilitate the ability to block or approve traffic based on the type of content. But no client system is able to access the originating servers on the internet directly. All requests are intercepted by the proxy, which then retrieves the content on their behalf and returns it to the requesting client. Now, while this adds an extra layer of processing, if you will, there are many advantages because the proxy server itself is the only system with direct internet access, and once the requested content is retrieved by the proxy server, it can cache that content so that if another client requests the same content, the proxy server doesn't even need to retrieve it from the internet. It's available from its own local cache. So all subsequent requests for the same content is delivered to the clients at LAN speeds instead of internet speeds. So that kind of configuration can be set up on just about any proxy server, but in some cases you might also configure what's known as cache-only proxies, which means that they are dedicated to only retrieving content and caching it. So they don't provide any kind of security, they just cache. But cache-only servers can greatly improve performance because they have a significant amount of storage dedicated to the cache, so that most internet-based requests can in fact be serviced from the local cache, which again greatly increases the speed of delivery as far as the clients are concerned. But when implemented for security reasons, which is typically their primary purpose, proxy servers can perform content filtering by literally examining the packets passing through them to distinguish between allowed and disallowed content. And since all HTTP requests go through the proxy, it essentially means that it's the only device allowed to connect through the firewall, making it the single point of contact to the internet, which inherently increases the security of your environment by allowing only that system to make an external network connection. Now, just quickly, because I did mention a firewall here, I do want to point out that a proxy server and a firewall are somewhat similar in that they can both allow or block content based on various characteristics of the traffic. But firewalls act primarily on port numbers and IP addresses in terms of filtering, whereas proxy servers can be configured to examine the content of the packets, such as the ratings of a site, keyword identification, and many other characteristics. But that key distinction is in fact the ability for a proxy server to examine the content of a packet, whereas firewalls usually act only on the information contained within the packet headers. Ultimately, when it comes to internet appliances, it effectively will depend on the type of service you need and the features provided by any particular make and model of device. So just be sure to consider all aspects of any given device before you purchase or implement. In this presentation, we'll talk about what are known as legacy systems, which quite literally refers to any system that is fairly old, outdated, or even unsupported. Now, any network these days can consist of a mix of old and new hardware, software, or services. In fact, I'd say that it's probably rare that any given network would have equipment that is all exactly the same age, with the exception of one that was just newly implemented or overhauled. But of course, it's really dependent on what you're doing, and more to the point, the specific services that are provided by the legacy system, device, or application. Now, while the legacy system might still provide a necessary service, you need to be mindful of some considerations such as the cost involved in maintaining them, as compared to the cost of upgrading to a new method or service. Now, of course, this will depend on what the system is for. It may be the case that it doesn't cost you all that much to keep it, but they could run proprietary software which may no longer be supported by the vendor or the original developer, or they may require specialized programmers to maintain them. Plus, it could be a situation whereby the longer you stick with the legacy system, the more difficult, time-consuming, and costly it will ultimately be when it does come time to upgrade to something new. But the reason why they tend to still be around is because they were built or designed for a very specific purpose. And it could be the case that there simply isn't anything else that is a suitable replacement, particularly if it was a custom-built solution. That said, as long as it provides the functionality you need, there is nothing that says you are required to upgrade. But that system might also represent a security concern because it may no longer support the most recent security upgrades or patches that are available. So you certainly need to be mindful of the versions it might be running, both in terms of its operating system and the applications, so that you can stay on top of any known vulnerabilities or exploits. That said, it might not be the case that the legacy system itself contains any confidential information, but if it's on the same network as all of your other systems, it could represent an easy target, so to speak, in terms of an intruder simply gaining access to the network first, then using that system as a means to compromise others. Other potential problems with legacy systems include possible issues with data incompatibility among the other systems that you might have, which might also result in making the legacy system unable to integrate with modern systems. And they might also result in your entire organization becoming out of compliance with governmental regulations or other governing bodies, all of which might ultimately or eventually outweigh the convenience of continuing to use the legacy system. Now, if and or when you do decide to decommission a legacy system, you may have to migrate any existing data onto a new platform, which typically involves several steps, beginning with extraction, which simply means to get the data out of the existing system in some kind of format that is manageable. Transforming and cleansing refers to converting the data to a type that is usable by the new system and removing any data that might simply be out of date, inaccurate, or just no longer required. For example, if it was a database, you could be storing customer information for entities that are no longer customers, or you may have to make changes to the format of data. For example, an older system might have stored only a 2-digit year in all date fields, which may now need to be converted to 4 digits. Validation refers to testing a subset of data to ensure that the transfer will go as planned, and if it doesn't, errors can be identified and addressed prior to attempting the full data transfer. Then finally, the actual transfer itself can be performed once validation indicates that no errors are occurring or that any previously identified errors have been corrected. Now, I should also mention a particular type or classification of a legacy system known as Supervisory Control and Data Acquisition, or SCADA, which refers to any type of system that is designed to gather and analyze data, usually from a variety of sensors, and most commonly used for monitoring and controlling operations of systems in a plant or a factory. That said, I should most definitely point out that any kind of SCADA implementation does not inherently mean that it is a legacy system as well. It's just that once implemented, the types of equipment found in places such as plants or factories tend to remain in place for a very long time. There would be regular maintenance and upkeep, of course, and likely even modular components that could be replaced, but the system as a whole tends to have a fairly long lifespan. So, if we look more closely at any given implementation, elements would include the ability to gather data both locally and from remote locations or devices. For example, a power company needs to monitor both the operations at the plant and the equipment in the field. That data must be monitored, gathered, and processed in real time, and you must be able to directly interact with the sensors through some kind of management application to configure how they collect their data from the various components they monitor. And all events must be able to be recorded in a log. Now, the point of saying all that is not to indicate that a SCADA application can't be brand new. Rather, once you do have all of that in place, for systems that are usually very specific in their operation, swapping it all out for something that's a little bit newer just isn't really an option. It's not like you're just applying a patch to an operating system. So, SCADA applications tend to be very complex and very specifically designed. Hence, once implemented, they tend to stay in operation for a long time. The primary components of a SCADA system includes the master terminal unit, which is where you oversee the system as a whole, monitor specific applications or individual components, and review the logs. The remote terminal units, which are essentially the sensors, and the human-machine interface, which allows the sensors to be specifically configured in the appropriate manner. Once implemented, SCADA systems can provide many benefits, including the ability to receive reliable and accurate information from your overall system, receive real-time notifications in the event that something does fail or requires attention, perform trend analysis to gain better insight into how the system has performed over time, and possibly get a better idea as to where improvements can be made, which can also translate into performing more proactive maintenance so that you can correct something before it fails or becomes problematic, which in turn can help to increase the lifespan of your equipment and allow you to make more informed decisions as you move forward. But there are also drawbacks, such as the potentially significant initial investment, the difficulty associated with adapting to a new system, as well as the amount of training it might take to bring everyone involved up to speed on its use. The support requirements after purchase and the time and money required to perform ongoing maintenance can also be significant, which again all relate back to the fact that once implemented, organizations are usually not likely to want to replace any of that anytime soon, leading to the fact that many SCADA systems can themselves be considered to be legacy systems. But that all said, as long as the system continues to do what it was designed to do, and as long as you're able to at least perform regular maintenance to ensure its long-term reliability, again, there is no reason to replace such a system simply because it's becoming a little out of date. Just always bear in mind considerations such as security and whether your aging system represents any significant risk to the rest of your operations. Ultimately, it really just comes down to the functionality being provided by this or any other type of legacy system, and if it's worth continuing to use and support it as compared to upgrading to something new. But at some point, every system will become defunct, so in that regard, it's really just a matter of when legacy systems should be decommissioned as opposed to if. For the final video of this course, we'll examine the Internet of Things, or IoT, which doesn't really refer to any particular thing. Rather, it's the extraordinary number of various devices around the world that are now connected to the Internet, all of which can gather, store, and share data. And this by no means refers to only what we might think of as standard computing devices such as desktop computers, laptops, tablets, and mobile phones, but virtually any device that contains a microchip, ranging from devices as small as a pill to the size of an airplane or a cruise ship. Ultimately, an IoT device is anything that can collect and transmit data to any other IoT device. An IoT ecosystem typically consists of web-enabled smart devices that use embedded systems, including sensors and communication hardware, to gather data from their environments. They can then share that information by connecting to some type of IoT gateway or other device which provides a means to store the data in a centralized manner for further analysis. In other cases, IoT devices simply communicate with each other and act accordingly without the need for any analysis, but it all depends on the services they provide. For example, in a monitoring application for a very complex system, sensors might be used to gather data, which would then be transferred, stored, and analyzed. But in a much simpler example, a device such as a security camera at home might recognize when a person is at your door, which then simply sends a notification to your smartphone. So no data gathering or analysis is required in that case, only an action is taken based on data input. Some common examples of IoT devices in daily life might include smart light switches and electrical outlets, thermostats, televisions, refrigerators, or smartwatches or health monitors. And I should point out that this is a very partial list, but in most applications, most or all of these devices can either communicate with each other or perhaps more commonly with a management application, usually installed on a device such as your smartphone or tablet, which allows you to configure and control each device centrally. For example, something like a smart home would allow you to control various lighting scenes, adjust temperature according to when you're home and when you aren't, monitor security and ensure that doors are locked, power appliances on and off, and many other services, all of which could be managed through a single application on your phone. In terms of industry, IoT systems can be used to manage, monitor, and control manufacturing, transportation, such as shipping and tracking, agriculture, such as controlling irrigation and pest control, and in healthcare, data from many types of sensors could be used to monitor a patient's condition and/or their symptoms, and that data could be fed directly into a centralized database to assist with diagnosis and treatment options. Finally, in terms of benefits, the Internet of Things can help people to live and work smarter, particularly with the multitude of health monitoring devices and apps that are available these days. Gain deeper business insights by providing real-time data into how their systems actually work and deliver services to their customers. And it can also greatly improve process automation for greater consistency and reliability, which can also provide greater transparency into customer transactions, which in turn can help to improve customer relations. Ultimately, IoT is becoming one of the fastest growing technological revolutions since the introduction of the Internet itself, and it will undoubtedly continue to grow at an ever-increasing pace. So, as you prepare for a career in technology, opportunities in the world of IoT will be plentiful, to say the least. So in this course, we've examined how to recognize and compare and contrast methods for wireless networking and the services provided by networked hosts. We did this by exploring wireless frequencies and channels, Bluetooth networking and long-ranged fixed wireless, 802.11 standards and NFC and RFID features, DNS and DHCP, server roles such as web, print, file, syslog, and email servers, the authentication, authorization, and accounting, or AAA framework, and Internet appliances, legacy systems, and IoT devices. In our next course, we'll move on to explore how to understand Internet connection types, network types, and common networking tools.